All right, we're starting chapter 5. Test is chapters 3, 4, and 5. 5 is starting to put together everything that we've talked about so far, both the descriptive statistics and probability. We learned the descriptive statistics, measures of center, measures of variation, and z-scores in chapter 2 and 3, and then talked about probability in chapter 4. So in chapter 5, we're going to start talking about using those descriptive statistics to predict what may happen in the population. Section 5.2 is random variables and probability distributions. Let's get those definitions. A random variable is a variable, typically represented by X, that has a single numerical value determined by chance for each outcome of a procedure. Now, the procedure may be that I'm going to flip a coin 100 times, and X could be the number of times it lands on heads. Or the procedure could be that I'm going to I'm going to survey everybody in here about your birthday, and X will be the number of people who were born in February. All right, so X is just a variable. It stands for something. It's a number determined by chance for each outcome of a procedure.
Before we finish this slide, let's skip to the next real quickly and let me tell you about a couple of different types of random variables, and then we'll come back to this slide. Random variables can be broken down and described as either continuous random variables or discrete random variables, and you should recognize the words continuous and discrete from chapter 2, I believe it was, or chapter 1. Continuous random variables may have infinitely many values. Those values may be associated with measurements on a continuous scale without gaps or interruptions. In chapter 1, we talked about continuous data being data that resulted from a measurement. It might be a height, or it might be time. We measure temperature, we measure weight. All of those were continuous data. Similarly, a continuous random variable results from a measurement. A discrete random variable has a finite or countable number of values. Most important word there being countable. Discrete random variables result from a count. So things that we count, like number of eggs a chicken lays in a day, or number of people who believe a certain thing, those are counted values, and so an X representing one of those counts would be a discrete random variable. Let's look at just a few examples of discrete and continuous random variables. Actually, these 5 examples say identify the given values as a discrete random variable, a continuous random variable, or not a random variable. Remember, a random variable has to be a numeric value determined by chance. So let's see if these are random variables, and if they are, whether they're discrete or continuous. The first one, the total volume of soft drinks that you consumed in the past year. That's definitely a numeric value. For each person, it would be determined by chance, and so it is a random variable. Would it be discrete or continuous? Well, do you measure volume or do you count volume? You measure volume, so the total volume of soft drinks that you consumed in the past year would be a continuous, because it's measured, random variable. What about political party affiliations of adults in the U.S.? Would that even be a random variable? Part of the definition of a random variable is that it's a numeric value, and political party affiliations are not numeric values. So we can't classify that as continuous or discrete. It's not even a random variable. shoe sizes of humans definitely are a numeric value. Would they be considered continuous or discrete? This one's a little bit confusing. I can see an argument for both continuous and discrete. Shoe sizes are measured, but they're available only in a finite number of sizes and to a finite level of precision. You can measure the length of your foot to an infinite level of precision, but your shoe size is either going to be, for example, maybe an 8 or an 8.5 or a 9 or a 9.5 or a 10. You can't get a shoe that's any more precise than a half size. So there's a finite level of precision there. And when you order a pair of shoes, there's a finite number of choices for sizes of shoes that you can get. So that is a random variable. It is a numeric value determined by chance, but there's a finite possibility there for a number of shoe sizes. So that is a discrete random variable. All right, the next two are easier. The number of movies currently playing in the U.S. There are either 300 movies playing or 500 movies playing or 400 movies playing, but there can't be 300.2759 movies playing at any particular time. There's a finite number of movies that are playing, and you count the number of movies rather than measuring them. So that is also a discrete random variable. And then finally, the running time of a randomly selected movie. It is a numeric value. It's determined by chance for any given movie. You measure time rather than counting time. So running time would be a continuous random variable. It's important that you distinguish between discrete and continuous, because in Chapter 5 we're only going to deal with discrete random variables. The number of peas that have green pods. Maybe it's 5, maybe it's 6, but it's not going to be 5.28. Number of babies with green eyes. Maybe it's 3, maybe it's 4, but still you count the number of babies with green eyes. So in Chapter 5 we're going to be talking exclusively about discrete random variables. Now let's go back to slide 6 and make sure you understand what a probability frequency distribution is.
A probability distribution is a description that gives a probability for each value of the random variable and often is expressed as a graph, a table, or a formula. Now, we talked about frequency distributions. These are going to look very similar, but we've talked about frequency distributions. This is a probability distribution, and I'm going to list all possible outcomes. Now, if there are 30 people in here, what are the possible answers to how many of you were born in February? What are the possible answers to that question? 30 or 0 or 1 or 2, anything between 0 and 30 could be the answer to that question. So if I was going to make a probability distribution like my frequency distribution, I would have to list 0 through 30. Those are the possible answers to the question, how many of you were born in February? And then I'd list the probability of each event. Sometimes the probabilities are the same for each event. Sometimes they're not. This is the one slide that I added, the one that you don't have, but it's okay. I just wanted to show you the difference between a frequency distribution, which we've already talked about, and the probability distribution, which is the main thing we're talking about today. A frequency distribution is, remember that table that lists all the possible outcomes and then the frequency of each outcome? This is rolling a die 60 times. And it looks like 8 times it landed on 1, 12 times it landed on 2, and so on and so on. That's the same kind of frequency distribution that we talked about. Gosh, I think that was chapter 2. Well, the difference between, well, one other thing, a frequency distribution gives the observed frequency of all possible outcomes of an event that's already occurred. We've already conducted an experiment or had a survey. These are showing the results of something that's already happened. That's descriptive statistics. When we make a prediction or when we give the probability of each possible outcome, that's called a probability distribution. And it gives us the probability of each possible outcome for an event that may occur sometime in the future. The requirement, let me go back. If this is the list of all possible things that could happen when you roll a die, it could land on a 1 or a 2 or a 3 up to a 6, and those are the only things that can happen when you roll a 6-sided die. And if this is their probabilities, what do those probabilities have to add up to? If this is the only possible outcomes, the probability that a die is going to land on either a 1, 2, 3, 4, 5, or 6 is 100% or 1, because that's certain to happen. Have you ever rolled a die and it just landed on an edge? Not going to happen. It's going to land on one of those 6 sides. And if you have a fair die, each one of the 6 sides has the same probability. So the 2 requirements for a probability distribution are the sum, remember this symbol, the sum? The sum of all the probabilities is 1. If this total doesn't add up to 1, then it's not a probability distribution. The other requirement is that each individual probability has to be between 0 and 1, inclusive, has 2 equals right there, because if each value in the right-hand column is not a number between 0 and 1 inclusive, then it can't be a probability. That was our definition of probability. Probability has to be between 0 and 1 inclusive.